So the first rule is, if you take a look at the constant rule, slide 3.3, uh, theorem 3.2, it's the constant rule. It says whenever you are trying to find the derivative of a constant, you'll get a zero. Okay, so this is oops, theorem 3.2. It says if you're trying to find the derivative of a constant, you'll get a zero. Okay, now what's that? That means whatever it is, if it's a constant, let's say 3, you don't need to do anything. You can straight away write a 0. And you can actually understand why is that. You can actually feel why that's the case. Can anyone tell me why do you think it should be 0? Just give it a try. Can you feel anything
Okay.
out there?
Doesn't it have to do with the way the derivative formula will work out later that it's it's like d of x, the derivative of that is 3 times its power, but its power in this case is 1 minus 1.
So that's the algebraic one. We haven't gone that far, to be honest. Um, let's say we haven't seen that. Now, can you feel anything? Can you imagine anything?
Constants are just reduced to 0 in this case.
Yeah, but the question is why?
I'm not sure.
Anyone?
Does it have something to do with like the graph? I remember like the tangents, it was like a constant line. So I don't know if that has to do with like zero change or something like that.
So if you go back to the definition of derivatives, uh, what can you remember? Just go back to the definition. Can you remember anything related uh, to the um, change of position or okay? What can you remember from the definition?
Is it the change in y of the change in x?
Um, yeah,
Isn't it the change of like the curve of the function at a specific given point?
yeah, I'll take both the answers. So the main thing is, if you remember, it's the instantaneous change of rate, right? So if you have a constant, so it that means it's not really changing, is it? Can you feel that? If it's a constant, then obviously whatever you had, whether it's velocity, whether it's the position, whatever it is, the derivative means you are finding the instantaneous rate of change. If it's a constant, then that means it's not really changing. So what should be the derivative then? It's 0. There is no change to the instantaneous rate and whatever it is. Whenever you try, whatever you try, it's a constant. That means it's not changing. That's why it's 0. Can you feel that? Try to feel that. Can you imagine this? That it's actually not changing. Do you agree?
Well, yeah, because you have a flat line, so there's no movement
Exactly.
up,
Yeah.
down, left, right.
Right.
It's a line.
Right. Exactly. So if you try to visualize it, a constant function, whatever it is, if it's, let's say, y equals, uh, let's say, y equals 3, okay? So this is my y equals 3. This is 3. This is 2, 1, 0. So it's never going to change, is it? So if you're trying to find the change, doesn't matter whether it's the instant change or whatever it is for a long term, it's always going to be 0. There is no change, right? So whenever I see a constant, but yeah, remember it has to be a solo constant. It can't have anything assigned to it. It can't have anything associated with it. It can't be the coefficient of any other term. It has to be a solo constant. Then you can write a zero. Okay. So let me see. Let me show you another example. What should be the derivative of this? And why? Excuse me.
Pi would just be 0 since it's technically a constant, or it could be represented as 3.14, and so have it. So 0.
Very good. So we know pi is a constant, right? I don't need to remember what the value is as long as I know it's a constant. I know pi is a constant, that's for sure. Whenever I see a constant, a solo constant, straight away, I'll say, hey, it's a 0 because it's a constant, right? Another example. Let's say it could be another good example of it. Okay. Oops, someone in the waiting room. Just give me a second. Okay, yeah. So another constant could be, yeah, let's say the speed of light. Okay. Or I might write a C here. The reason I'm not writing C here, generally we denote it by C, but I'm not writing a C here because our formula says C for constant. So, and that's actually for any constant. So I'm not really using it. So let's say the speed of the light. So the light has a constant speed in vacuum, of course. It's not really everywhere because if it has any other obstacles, then the speed definitely gets decreased. But if you have a vacuum place, this light has a speed which is constant. So again, you can straight away say it's 0. So that means what I'm trying to signify here, well, whenever you see a constant and you are asked to find the derivative of it, you just don't worry, don't need to do anything else. Just write a 0. And we'll use it several times, trust me. But yeah, again, it's really easy to get carried away. Okay. And use it in the wrong sense, because if you see anything like this, 3x or something, this 3 is a constant. So I've seen students straight away writing a 0, just when they start using these theorems. As I said, I'm repeating again, the constant has to be a solo one. It can't be assigned to anything. It can't be the coefficient of any other variables like this. Okay. All right. Any question from this? No questions at all? Okay, so let's go to the next one then. Oh, this is the graph. In the next slide, you have a graph which is quite similar to the one I showed a couple of minutes back. Okay. All right. The next theorem, it's theorem 3.3, the power rule. Okay. So it says if you have a function, let's say x to the n, where n is the exponent or the power, then the derivative of that is the exponent comes in front. It actually comes in front. And then the power gets reduced by 1. So whatever you had, again, someone is in the waiting room. Give me a second. Oh, 2 people are waiting. Sorry. Sorry about that. Cooper and I forgot your name again. Maybe Tolope or something like that. If I'm pronouncing your name wrong, please correct me. Sorry about that. I was doing a problem, so I couldn't really see that you guys were waiting in the waiting room. Sorry about that.
Okay, sir, no problem.
Okay, thank you. All right, so whenever you have a power function like this, so the derivative of it is obviously the exponent will come in front, and then the exponent of the original power function will just get reduced by 1. Okay, let me show one example, and it will be easier to understand. It will be easier to digest. Okay, let's say I'll start with an really easy one. So let's say I need to find the derivative of x cubed. Okay, so what's the value of n here?
In the example, would be 3, wouldn't it?
3. Okay, right. So n is 3 here, right? So we know that n will come down here, right? Then we'll have the function, and now the exponent will be 1 less. So it will be 3 minus 1. So the derivative of x cubed will be 3x squared. Any question from this?
What if you had a negative exponent?
Very good point. Oh, again, someone is in the waiting room. Give me a second. Okay, so this is actually true for any value of n. So if you go to the slide, it says that if n is a non-negative integer, then it's true, but you will see examples where we can use this. But yeah, the thing is, let me show one first. Let's say I have x to the, that's the negative 3, okay? So when you try to find the derivative of it, you'll see this is actually true for negative exponents as well. I'm just using the same formula. It will actually be like this. They said n has to be non-negative, okay, but it's actually true for any value. We'll see some exceptional cases later on, but as you can see, there is no harm in doing negative exponents either. I'm sure they have showed something for the negative as well. We'll slowly but surely go there, no worries. But you can trust me. This is also true for a negative exponent like this as well. And you can verify it online, okay? Okay, so this is the rule we'll use probably the second most time. Now the question could be, which formula will be using the most times? The answer is the next one. No, not the next one, sorry about that. It's theorem 3.7, not the next one, sorry about that. So we'll be using theorem 3.7, I believe, the most of the times. But we'll be using this one as well. We'll be using this theorem tons of times, probably 1,000 times if you practice those number of problems. Okay, so you need to remember this formula. It's pretty straightforward as long as you can keep that somewhere in your head. Okay. All right. Any other question from this?
Is that all there is to finding derivatives, just this simple formula? Or so this will work on any derivative no matter the complexity of the thing we need to derive?
Well, as long as it's a power function, it will definitely work.
Okay.
But it can't be like this. It can't be like this. That means you need to have a constant or value here. I mean, here as the exponent, this n can't be the variable. That means like this, in this one, I have, it looks like, looks pretty similar, right? But here you can see I have x as the exponent. I have the independent variable. I mean, in terms of what I was actually trying to find the derivative. I have this independent variable as the power, as the exponent. If that's the case, we can't really use the power rule. As a power, this n has to be a non-negative, a value. It shouldn't be, it doesn't need to be a non-negative integer, as I said, but yeah, it has to be a value. It has to be at least something else other than these variables. It can't be the variables. Not only x, it can't be any variable. It can't be x, y, and the traditional variables we use, t. It has to be values like this. I mean, 3, 4, 5, or -4, 5, 6, or it could be any other constants. Let's say x to the pi. That's still fine. If it's even like this, x to the pi, I'm really bad at writing pi's. Yeah, it looks good. Okay, so if it's like this, then it's still okay. But again, it can't be like this: x to the y, or y to the x, t to the x, x to the t. It can't be variables like this. Okay. And you will see more examples. Hopefully, it will make more sense. But did it answer your question?
Yeah, I think that answered the question that I had. So thank you.
Thank you. Okay. Now, let's go to the next one. Meanwhile, as I said, if you find any question, just unmute yourself whenever I am not really discussing anything, or you can have it written in the chat section. I'll try to keep an eye on that. Okay. This is the real business. Okay. We have started the real calculus one. And things will be definitely complicated, but it will be fun. It will be really, really interesting to solve these problems. And we'll be doing lots of derivatives, okay? Here on the discussion, in the homework problems, in the exam, we'll be doing tons of derivative problems, okay? All right, let's move to the next one. It's 3.4. Theorem 3.4, by the way. And it says, it's the combination, you can say a slight mixture of theorem 2 and theorem 3.2 and theorem 3.3. That means if you're trying to find a derivative of a constant times another function, it may or may not be a power function. It could be any function. If you have a constant times another function, the thing is, you will always keep the constant outside and just find the derivative of the main function. Okay. Let me show you one example. Let's say we're trying to find, let's try the mixture of those, 3x cubed. Okay. So you can clearly see that it's a constant and it's another function. Constant times another function. Okay. And what the theorem says, you can always keep the constant outside and then find the derivative of the main function. And what's the derivative of x cubed? If you remember, we have just solved it.
3x squared.
Exactly, 3x squared, right? Using the power rule. Oops, what's this red line? Sorry about that. So we know the derivative of x cubed will be 3x squared. So the product now, or if we simplify it, will be 9x squared, and that's the derivative of this function. So that means whenever you see a function with a constant multiplied to it, you can just keep the constant outside and find the derivative of the main function. And then you can simplify once you're done. That's kind of normal algebraic approach, right? Multiplying or simplifying an expression. Any question from this? No questions at all? So what I want you guys to do now is to solve a problem for me, just a practice problem, and I'll give you 1 minute for it, okay? So let's try this one. Okay, can you solve it for me? Can you find the derivative of this function, -3/2 x to the 7? Can you do it for me? Just to write the answer in the chat, that will be fine. Okay, and I'll ask you, how did you find that? I mean, what led you to this solution? Which formula have you used? Okay, and your time starts now. Okay, I think your 1 minute is almost over, and I can see most of you, although you can see the other answers as well and what others are typing. But again, if you're just trying to copy others' work, you'll have only yourself to blame, right? You're here to practice, we're here to learn. So even if you get it wrong, you should try at least to see where do you stand, right? Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 out of 15 answers. I think that should be fine. Let us go for the solution. So I'll go for some random pickup from the chat list and ask you, how did you find it? Okay. Okay, so let me see. Okay, so Justin, can you tell me, how did you find -21 over 2x to the 6th? How did you find that? Can you tell me? Justin?
Can you hear me?
Yeah, I can hear you, yeah. I don't think I can hear you now. Can anyone else hear him?
Yes. I can explain it.
No, I mean, can anyone else hear what Justin was trying to say? Because I couldn't.
Yeah, I didn't hear him either.
Oh, okay. Okay, yeah, I think you can go ahead. You can explain how did you get that.
Okay, using the formula of differentiation, which typified nx raised to power n minus 1. So from the question, -3/2 x raised to power 7, then we will differentiate it by multiply 7 with -3/2, then subtract 1 from 7, which will give us 7 times -3/2, which will give us -21/2 x. Then 7 minus 1 will be equal to 6. So it will now be equal to minus 21 over 2x raised to power x raised to power 6. That's how you get it.
Very good. Yeah, thank you. So what you have done here, if you have done it, or if you haven't done it, you can clarify your concept now. So again, using the previous theorem, we can keep the constant outside, right? We don't need to do anything with this. And the next thing we need to do is to find the derivative of the main function, whatever it is, whatever associated with the constant. And using the power rule, using the theorem 3.2, I believe, or 3.3, we can find the derivative of x to the 7, which is n x to the n minus 1, right? Where n is 7. And if we can simplify it, we'll get 3 times 7, which is 21, and x to the 6. Is there anyone who is still confused? I'll be more than happy to, excuse me, to try to convince you, try to make you understand with probably some other examples. No questions at all? Okay, let's move on then. The next one we have is theorem 3.5. Theorem 3.5. And it will help us to find derivatives of more than one function, okay? And we'll use it several times as well. This will be really helpful. Let me show the theorem first, and then we'll see examples, okay? So let's say we have two functions. F and g, where both f and g are differentiable, okay? So it would be the sum of the derivatives, individual derivatives of these functions, okay? Now, what does this mean? That means if you have more than one functions, it's actually true for any number of functions, okay? As long as you have more than one functions, you can actually use it. So if you have more than one functions, and if you're trying to find the derivative of the sum of those functions, that means you are adding these two functions, or three functions, or four functions, how many, it doesn't matter how many you have. If you add these two functions, okay, and try to find the derivative of that, it's actually the same if you find the derivatives of those functions one by one and then add those, okay? Let me show you one example. It will be really fun. I think you have seen something similar for the limit as well, right? When you had the sum of the limit and the limit of the sums. It was the same. So it's the same here as well. Obviously, as long as both f and g are differentiable at that, at that particular point. I guess someone unmuted himself or herself. Do you have any question? Any question you might have? If there is any, you can unmute yourself. Okay, no questions. Seems like there is no question. So let me show one example and then I'll give you a chance to ask questions. Okay, no worries. So let's say our first function is x squared, and our second function is let's say x to the 5th. Okay, and we're trying to find the derivative of these two functions. I think I should try easier ones. Yeah, I shouldn't try complicated ones to start with. Yeah, let me try this. So let's say we have 3x minus 1 and we have 3 minus 4x. Let's say we have something like this. Okay, now on our left we are trying to find, again, if you don't understand my handwriting, just let me know. Okay, so first of all, we'll be trying to find the derivative of the sum of these two functions. Okay, so if we add these two, we'll get 3x minus 1 plus 3 minus 4x. We'll just add this first. Okay, so if we add this 3x minus 4x give us a minus x, right? I'm just doing some algebra here, nothing else. No real calculus here. This 3x minus 4x, it's just negative x. Do you agree? And we have negative 1 plus 3, so that's plus 2. Any question up to this? I've just added these two functions, or those two functions, I would say. Just simple algebra. Any question from this? Take your time, okay? You don't need to digest all this in the first instance. You can still take time, and probably after a while it will make more sense. Okay, now let's do that, or even, yeah, okay. So now I think I should have tried. Yeah, let me make adjustments so that it makes more sense. Yeah, instead of 3, let me try with 1 here, so that it becomes 0. It will make more sense, because if I want to do anything with more than one term, then I actually need to use the same theorem, which I want to avoid when I'm trying to prove that it's true. So let's say my function was 1 minus 4x. So this negative 1 and positive 1 will cancel out each other. So I'll have a negative x. So what's the derivative of negative x? Can you do it for me?
Minus 1.
And how did you get that?
We'll find the derivative using the principle of differentiation. We get minus 1, because that minus 1, it's typically raised to power 1, but they do not write it there. So minus 1, that 1 minus 1 in the rules of differentiation, we have nx, n raised power, nx raised power n minus 1. So 1 minus 1 will automatically become 0. So anything raised power 0 is equal to 1. So it's going to be negative 1.
Very good. So we actually, what you can do, this negative 1, let me rewrite it first. You don't need to do that. I'm just trying to show. This negative 1 can be written as negative 1 times x, right? And using the previous theorem, where if you have a constant, you can keep the constant outside. So negative 1 is a constant. I can keep the negative 1 outside. Again, I'm just showing all the steps. You don't need to show all the steps. Okay. And this x can be written as x to the 1. Do you agree? If there is no exponent, that means there is a 1 here. And if I use the power rule, the n is 1 here. So 1 times x to the 1 minus 1, right? So negative 1 times x to the 0. What's x to the 0? Anything to the power 0. Anything to the power 0 is always, excuse me, is always 1. So it will be negative 1. Anything to the power 0, even 10,000 to the power 0 is actually 1. Anything, whatever you take. If you are upgrading it to the power 0, it will always give you 1. Now, any question from this? Any question? No questions at all? Okay, then. So let's see the right-hand side now. I mean, if we find the derivatives of this separately, then what happens, right? ddx of f of x first. What's the first function? It's 3x minus 1. So ddx of 3x minus 1. Oh gosh, I need to use the same formula. So we know the derivative of a constant is 0, right? So we can avoid it. So the derivative of 3x I'll keep the 3 outside. Oh, it's not a good example. I'm sorry about that. That's the problem when you try to generate one instead of having one already. Okay, no worries. Still, it still works. It will still make sense. So the derivative of x, we have already seen here that the derivative of x is 1. So the derivative of the first function is 3. Now the derivative of the second function. Okay. And it was, I guess, 1 minus something. 1 minus 4x, yeah. And again, the derivative of a constant is 0. So we can only just find the derivative of negative 4x. And using the constant rule, again, we'll keep the constant outside and find the derivative of the other part. And again, the derivative of x we know is 1. So the derivative of g, the g function, is negative 4. Now if we add these two, ddx of f plus ddx of g is 3 plus -4. That means 3, -4, -1. And you can see it's exactly the same as this. Any question from this? I know it's not a good example, but it actually makes sense because you can see if we add these two and then find the derivative, or if we find the derivative of these functions and then add those two, we actually get the same result. No questions at all? Okay, let's move on then. The next one we have is the definition of the number E. Okay, so what I want to do is to take a break for 5 minutes now, and then we can start from the next slide, which is the definition of the number E. Okay, so let's meet at 10:06 and we'll start with that. Okay, I'll see you in 5 minutes. Do you have any question from the discussion we have so far? We can try this first if you have any. No questions at all? Okay. Let's move on to the next slide, I mean, next topic, which is E, the number E. Because I've already shown you something like that, that if you have anything of this format, we can't really use the power rule. That means there has to be something else which we can use, or rather, I should say, there is another formula which we can use to find the derivative of a function of this format, right? And for that, we first want to know the significance of the number E. So what does it mean? So if you have E, you can actually find there is a certain number assigned to it. Okay, that means if you plug in E in your calculator or if you search online, you will see it actually has a fixed value. It's a constant, okay? And the value is 2.718. I just take 3 decimals, up to 3 decimals. You can actually keep going on, okay? So it has a fixed value. So first of all, it's a constant, no doubts on that. But if it's the base of any exponential function, then we actually have different results. That means if you can express it like this, e to the x squared, e to the half x or something like that, that means if it's the base of any exponential function, then it actually gives us some really interesting results. We'll see some of these very soon. So what happens if we have e as the base of these type of exponential functions? So then we have a certain rule for it. If you have anything of this format, it will always return you the same function. But only if and only if there is nothing here. We'll see examples as well, where you'll have something assigned here as well, like this one, like we have a -½ assigned to this x, or we have an x squared instead of x. Okay, you will get the same thing only if you have a solo x here. Now, what happens if we have anything else? We'll see that as well. As I said, no worries. And I want to show that here. I want to, maybe they have it in the later in slide later on, but I want to show it now so that it makes more sense. So if you have anything assigned to it, let's say e to the mx, what kind of sign is that? Okay, so if that's the case, then the derivative is m times e to the mx. That means you still get what you have here, you still get that, but since you don't have a solo x, instead, what's that? Instead, you have another constant or coefficient assigned to it that will come down in front. Okay, again, for e to the mx, for any value of m, you'll get e to the mx, but this m will come in front. As you can see, you might get it mixed with this formula. It's not the same, by the way. Right? It was actually one less than the exponent. Whereas here we have the same exponent, right? Let's see one example of it. ddx of e to the, let's try with that example. We had -½ x, okay? So using that formula, we can straight away say, hey, my m is -½ here, right? This is my m, and I know the m will come in front. So this is my -½ this is my m, and then whatever I have, I can just copy that, -½ x. Do you agree? So this is my m, and this is my entire function, which is e to the mx. Do you agree?
So just to make sure I'm getting this right, in the case of e to the x, where x has a constant power in front of it, in this case -½ you just copy that in front of e.
For the e to the x squared?
Was that e to the x squared? Because it's e to the -½ x in this case.
I mean, are you talking about this one?
Oh, okay. Yeah, I see what you're saying now.
So that's actually another example. We haven't gone that far.
My bad.
For finding derivatives of this function or this type of function, we actually need some more concepts, some more formulas. We haven't gone that far, but if you have anything like this where m is a value, I mean, this x has to be linear. That means the power of this x can't be more than 1 if you want to use this formula. Yeah, I think I should mention this. So no, I think I already have it clear, because this x is fixed. You can't really change it. Only thing you can change here is m. So whatever you have in place of m, you can just write that in front and then copy the entire function with that, like this. Let me show you another example. Hopefully it will make more sense. Let's say we have e to the, I should try something positive sometime. So 4x, okay? Again, this is in the form of e to the mx, right? And we know whenever we have e to the mx, it looks really clumsy, isn't it? Let me remove some of this. Okay. All right. So whenever we have something in the form of e to the mx, we can straight away write m times e to the mx, right? So here, what's the value of m? Anyone?
4.
What's the value of m?
4.
4. Very good. So, what? Someone's in the waiting room now? Oh, it's Tolope. He was here. When did he leave? When did he leave? Anyway, so here m is 4, and I know that I can write m times e to the mx. This using this formula, right? And that's it. That's my answer. So whenever I see any function of this format of e to the mx, I can use this formula and write m times e to the mx. Any question from this? Take your time and see if you have any question. Again, this is just the beginning. We'll definitely have more complicated problems. Things will get much, much more sophisticated. Okay, but we'll be using this basic theorems, I would say, because they have mentioned it as theorem, but you might say formula or methods, whatever you feel right. We'll be using this even in those sophisticated ones as well. Okay, so the basic idea will still remain the same. We'll be just getting some more things to do. Instead of getting the answer in one line, we'll be actually doing several calculation and then use this probably at the very last or something like that to get the result. But again, as I said, we'll be using this most of the times, probably all the times. Okay. Any question from this so far? Am I going too fast? If you want me to slow down just a little bit, you can just say that, or you can ask questions so that we can spend time on that, or you might say give us a break so that we can understand what's going on. If you feel that I need to go just a little bit slow, just let me know. All right. So let us go for the next one. Okay. The next one is for the higher derivatives. That means what happens if you have more than one, more than, if you have to calculate the derivative more than once. Okay. If you remember, I stated it a couple of times the last time that we are calculating the first derivative, right? So that means we can actually calculate derivatives for more than once. We can calculate the second derivative, the third derivative. I mean, obviously, if you can understand, obviously we can do it as long as it's differentiable that much time, right? We can't really define, or we can't really find the derivative of a function which is not differentiable. So if we are trying to, let's say, the fifth derivative, then that means it's differentiable 5 times. If it's not differentiable 5 times, we can't find the fifth derivative, right? We already know that when we're trying to, again in the waiting room, really? Just give me a second. I guess he's having some technical issues. So. All right. So we know that when you're trying to find the first derivative, the function was actually differentiable at least one time. That's why we tried to go for it, or rather we went for it, since it was differentiable at least once. If we're trying to find the second derivative, then it's definitely differentiable at least twice. Okay. All right. So what's the rule then? The rule is exactly the same. We just need to keep doing that. That means if we have a function, let's say, sorry. If we have a function, we know that it can be written as this, right? It's f prime, or in some cases, you'll see someone writes as to make it more understandable. Someone writes it's f1x. Generally write f prime. That shouldn't be a problem. Okay. Now, if we're trying to find the next derivative of it, what we want to do is just find the derivative of the first derivative. This way we'll get the second one. Okay. And we can keep doing this as long as it's differentiable, as I said. So that means whenever you're trying to find a derivative, let's say the nth derivative, all you need to do is to find the derivative of the or rather up to the previous power. That's it. I should write ... here. That means it's true for any number. As you can see, when you try to find the second derivative, all we did is to find the derivative of the first derivative. We differentiated that again, right? That means if you're trying to find the nth derivative, you just differentiate the n-1 function again. That's it. That means, in other words, if I try to reiterate it. If you're trying to find the fifth derivative, okay, f5, should write a parenthesis here. All you need to do is to find the derivative of f4, right? And you keep going backwards to find the exact value. That means for finding f4, what do you need? You need the derivative of the third one, right? And you keep doing it. You keep going backwards to find the values, right? You just keep differentiating it, nothing else. So when I say find, let me show you just one example, because we'll see it later. We don't want to go too deep into this right now because we'll be mostly doing first derivative in the next couple of slides, but we'll return to these higher derivatives later on. So let's say I have a function. I'll start with the same one, x cubed. What's the first derivative of it, if you remember? Anyone?
3x squared.
3x squared, thank you. Let's say I'm saying, hey, can you find the second derivative for me?
6x.
The second derivative is the derivative of the first derivative. I mean, if you differentiate it again, and again, 3 is a constant, you can keep it outside. And the derivative of x squared, what's the derivative of x squared? Anyone?
2x.
Right, using the power rule, right? The 2 comes in front, and it's 2 minus 1, so 2x, which is 6x. And then I might say, hey, can you find the third derivative for me? And the answer is yes. We need to just find the derivative of the second derivative, right? And using the constant function rule, we can keep the 6 outside and the derivative of x. And we know the derivative of x is 6, x is 1. So it's 6. Now, if I say, can you find the fourth derivative for me?
0.
Very good. So I just need to find the derivative of the third derivative, okay? And it's a constant. It's a solo constant. We know the derivative of a solo constant is actually 0. There you go. So the fourth derivative is 0. Right? So you can see we can keep doing it as long as it doesn't become 0. If it's 0 for some derivative, then it doesn't really make sense if we go further, because finding the derivative of 0 will always be 0. So once we get 0, we stop. Okay. So you can see this function is differentiable 4 times. This function is differentiable 4 times, right? Do you agree? And we do get the fourth derivative, which is 0, in fact. We actually can do it. And you can see we have just used the same basic idea. We haven't done anything else, right? Any question from this? Take your time and see if you have any question.
I do have one question.
Sure.
So I get how you can go like each derivative. That all makes sense to me. But if we were given a problem and it just had the first equation that you gave us and it said find the derivative, would you want us to derive it until we couldn't, or
Yeah,
just?
would you please repeat the question? Sorry about that.
Yep. So like if we were given just the first equation of this and it said like find the derivative of this problem, would you want us to go all 4 steps and find each derivative, or do we stop after the first
So
Just
if I
find f(x).
just say find f prime x, or if I just iterate or rephrase it as please find the first derivative, then obviously stop here.
Okay, but you would say like keywords like first or like find the third.
Yeah,
or
definitely,
something.
definitely.
Okay, awesome.
I definitely mention it if I want you to calculate any higher order derivatives. If I want you to calculate the third or the fourth derivative or even the second derivative, I'll definitely mention it. Okay, any other questions? No questions at all? Okay. Let's go to 3.4. And here we'll learn the product rule. And as I said, we'll be using this rule in my guess, we'll be using this one the most times in this summer course. Okay, especially in the derivative part, not in the integration part, but in the derivative part, we'll be using it tons of times. Okay, tons of times. So let's try to understand what's going on, and then we'll see some really good examples of it. Okay. All right. So the product rule is it's not exactly the way we have done the sum rule. Let me take you back to the sum rule. This one, where we had just found the derivatives separately and added those. The product rule doesn't work that way. It's not that straightforward. Okay, let me write the product rule for you. Product rule. Okay, it's 3.7. Excuse me. Excuse me. Okay, so the product rule, if you have two functions f and g where both of these are differentiable at x, then what we do is d dx of fx times gx, that means the product of two functions, is actually the derivative of, I mean, if you just keep the first term and find the derivative of the, keep the first function and find the derivative of the second one, plus keep the second one and find the derivative of the first one. I think I should change the order of this. Yeah. Yeah. So that's exactly the same thing anyway. So what we do here is, if we have more than one functions as a product, what we do, we keep one and find the derivative of the other one. Then we keep the other one and find the derivative of the first one. Whichever order you do doesn't matter, as long as we are adding these two, right? Now let us see one example, and hopefully it will make more sense. So we have, let's say, f of x equals x cubed, g of x equals to, let's say, 3x. Okay. So what it tells us, if we just multiply these two first and find the derivative, so x cubed times 3x, which is 3x to the fourth, okay? And it's a constant, 3 is a constant, so we can keep that outside, and we can find the derivative of x to the fourth. using the power rule, the power comes in front, and here we have one less, right? N times, we are using this formula, n times x to the n minus 1, where n is 4. Do you agree? If we can simplify it, sorry. We get 12x cubed. I'm just showing that this formula holds, okay? And because we'll be using this for more complicated problems. Okay, so that's the left-hand side. Now we want to find this. So first we'll keep one function and find the derivative of the other one. So f prime x gx, that means we'll keep gx as it is and find the derivative of f. So f was x cubed. What's the derivative of x cubed? And as I said, we'll keep
3x square. 3x square.
gx was 2x, or gx was 3x. Sorry about that. As I said, gx will be kept as it was. We'll just find the derivative of the first one. So the derivative of x cubed using the power rule again is 3x squared, right? N times nx to the power minus n. And we have a 3x here. So if we simplify it now, 3 times 3 is 9. X cubed times x is x. X squared times x is x cubed. Do you agree? Do you agree to this calculation?
Yep.
Okay, let's do the other one. Now, we want to keep the first function and find the derivative of the second. So let's keep f of x and find the derivative of g, the function g. So f of x was x cubed, we'll keep that and find the derivative of the second function, which is 3x. What's the derivative of 3x? 3 is a constant. Using the constant rule, we can keep it outside. And the derivative of x, right? We know the derivative of x is 1. So x cubed times 3, if we simplify it, it's 3x cubed, right? Do you agree? Before we go any further, do you agree to this calculation? Is there anything you want me to explain? Anyone?
There's a mistake in the solution, I think. The x raised power 3, when you differentiate it, should be equal to should be equal to 3x square. You write 3x cube.
Which one? Sorry. Which part? Sorry again.
What I'm saying is that the final answer, the 3x cube, should be 3x square. When you differentiate it,
This one?
when you find the derivative of 3x cube, should give you 3x square, and you write 3x cube.
On my right, here?
Yes, your final answer.
I didn't differentiate x cubed here. As I said, I'm keeping the first function.
Oh, okay. You multiply it. Okay. Oh,
Right,
I'm sorry.
right, exactly. No problem. No problem. Yeah. So now we'll be adding these two, as the theorem says, we'll be adding these two parts and see what happens. So if we add these two, we have 9x cubed plus 3x cubed, which is 12x cubed, and it's exactly the same as this. That means this theorem holds. Now, any question from this? Let me show you the calculation again. Yeah. Maybe minimizing it gives you more space. Yeah, right. Yeah. So just take a minute and see if you have any question. It's just a formulation. I'll show more examples. How and when can we use that? Okay. Just take a minute and see if you have any question from this calculation. No questions at all? Perfect. Let's move on then. Okay. So let's
One
see.
question about
Yeah, sure. Yeah.
your notes. Is it possible for you to make them into like a PDF and upload that file so we can study off of that too? I don't know if
These
you can do
files?
that with the Notes app.
These files on the iPad?
Yeah.
Yeah, I think I can do that. Yeah, I think I can do that.
Awesome.
Yeah.
That would be great. Thank
Okay,
you.
okay, yeah, sure. I'll do that from now on. In most cases, I haven't really shown that much, but today I think, yeah, I have shown enough examples. Yeah, at least this file. Yeah, I'll definitely add it. I'll definitely add it to the modules. Okay. All right. Now let's see an example. How and when can you use that? Okay. So let's say I have a function. Let's say I'm trying to find the derivative of e to the 5x times 2x plus. Let me start with an easier one. I don't want to complicate things too much now. Let's say it's x to the 6. Okay. So we want to find the derivative of this function. Okay. And as you can see, this function has two parts working as a product. So we can use the product rule now. Whenever you see this, when a function can be subdivided into two parts or more than one parts, where they're working as a product, we can actually use the product rule to make our life easier. Okay, let's do that. So obviously, what we'll do, if you remember, let me have it here. So when you have two functions, you just keep one and find the derivative of the other. Okay, and then add those. Like this. Okay, so keep one, find the derivative of the other, and do it for the other function as well. Keep one and find the derivative of the other, and then add those. Okay, so what we'll do here, we'll keep x to the 6th and find the derivative of e to the 5x. Oops, sorry. What's the derivative of e to the 5x? Anyone? We have seen this. We have seen
E to the 5x would be 5e to the 5x, right?
5s with 5s.
yeah. So for your convenience, let me have it here. E to the mx, any function of the format e to the mx will in return give m times e to the mx. Okay. So here m is 5, so it will be 5 e to the 5x. And obviously there was x to the 6 multiplied with that. Okay. So that's this part done and dusted. We'll now do the other part. So this time we'll keep e to the 5x and we'll find the derivative of the other function. Remember, you have to do it in the single line. You can't do it separately. Okay, show it on the same line, like I'm doing here. Okay, what's the derivative of e to the x to the 6? Let me have the formula again for you.
It
DDS.
should be 6x to the 5 to the 5th power, I guess.
Exactly, yeah. So we know the exponent comes in front and we have one less exponent. The exponent gets one less than the original one. So n x to the n minus 1. So 6x to the 5th. So now if we simplify it, we get 5x to the 6th e to the 5x plus 6 x to the 5th e to the 5x. So that should be your answer. You can still simplify it further. You can actually factorize it, but that is not really mandatory. If you can do that, that's fine. If you can keep it like this, that's still fine. Any question from this? Take your time, okay? Just try to see the calculation again. I have the formulas I have used. Try to see if you can generate any question, if you find anything which doesn't make sense to you. No questions at all? Okay. So what I want you to do now is see another formula, which is the quotient rule. Okay, and then I'll show an example of that as well. Or maybe I can do something else. Maybe if you want, I can show a couple of more examples of the product rule and leave the quotient rule for Monday. But your homework 3.4 is due on Tuesday, which I believe has some questions from the quotient rule. So that would be another problem though. Yeah, I think I should go for the quotient rule. Then if you have any problems from the product rule, you can send me emails and we can chat about it, okay? Because if I just leave this one rule, then the homework can't be completed. The quotient rule. Now, instead of a product, we'll have the ratio of two functions, okay? And we want to find the derivative of it. And it's quite similar to the product rule, okay? Quite similar. But here, in addition to that, we'll have a denominator. We only had a one-way traffic here, But for the quotient rule, we do have the denominator, okay? And again, we'll be doing the same thing. We'll be keeping the first function, one function, and find the derivative of the other, okay? But instead of adding this, we'll have a minus sign in between, okay? We'll be subtracting this. Here, if you just compare it with the product rule, we actually have three things to take care of. So let me have the product rule here for you so that you can see what are the three things we can take care of so that we don't get confused or don't do any mistake. Okay. Let me write it in the same order so that it makes more sense. Okay, so the first thing is we'll be definitely doing the same for the quotient rule as well. That is keeping one and keeping one and finding the derivative of the other, and we'll be keeping the other function and find the derivative, keeping the first function and find the derivative of the other. What we have done here as well, you can see gx f prime x fx g prime x. It's the same again, you can see gx f prime x fx g prime x. So we'll be keeping one and finding the derivative of the other. So this part is exactly the same. But for the product rule, we can change the order. That means we can first do this part and then do this part, and we'll get the same result. That means we'll do this part and then add this part with that, we'll get the same result. But for the quotient rule, you can't change the order. You have to do this part first and then subtract this part from the first one. You can't change the order. Okay, this order has to be maintained. That means you need to keep the denominator and find the derivative of the numerator first, and then subtract this one. That means keep the numerator and find the derivative of the denominator. Okay, and you can clearly understand why. Can you unmute yourself? I don't know where the background noise is coming from. Tulope, can you unmute yourself? Thank you.
Yeah, I'm sorry for distraction.
No, it's okay. It's okay. I understand. Okay. So in the product rule, which where you find the product, it doesn't really change anything, you know, because 3 times 6 is 18. 6 times 3 is also 18. So if you change the order, it doesn't really change the value, right? You can actually change the order, no problems with that. But that is not the case with the quotients, right? If you divide 6 by 3, it gives you 2. If you divide 3 by 6, it gives you half. So you can clearly see changing the order here matters. So that's why you can't really change the order here. So what you need to do is just, let me use this so that it doesn't become too clumsy. Okay, so you just need to find the derivative of the numerator, okay, and keep the denominator, and then keep the numerator and find the derivative of the denominator. You have to maintain this order, okay? So that's the first thing. You have to maintain it. You have to maintain this order. What's the second thing? In the product rule, we added these two, whereas in the quotient rule, we'll be subtracting it. Obviously, we have a certain order. That's the first thing. Then the second thing is, instead of adding those two, we'll be subtracting. We'll be finding the difference between these two. Okay. And the third one is, we have a denominator here, and in the denominator, we will not be finding any derivative. We'll just have the square term of the denominator, nothing else. We'll not be finding any derivative in that. Just have the square of the denominator. Okay, this way you can remember these two simultaneously and don't get mixed. I mean, you don't mix any of these to the other one. Okay, let's see one example of it. Obviously, you need to remember it. Again, I'll ask the course coordinator whether I can provide you with the formula. I wish I can, because if you understand what's going on here, that should be fine. I don't think memorizing it is the main part here. Okay. All right. Let's see one example. So let's say we're trying to find the derivative of, let's try an easy one. Okay. X cubed over, let's say, no, I'll take e to the 4x over x squared. Okay, let's try to find the derivative of this. Obviously, you can see the formula, so let's do that. What's the first thing we need to do? Anyone? Just eyeball the formula.
You can do the derivative of the top and keep the bottom. So you'd have 4e to the 4x times x squared. And then you subtract e to the 4x times 2x. And then you just have the denominator squared. So you'd have x squared. So.
Do you agree? Let me explain what we have done here. Okay, let me show it one by one. I'll have it here, but I'll show how the steps were done. Okay, so ddx of e to the 4x over x squared, the first thing is we keep the denominator and find the derivative of the numerator. Okay, so let's do that. Denominator is x squared, right? Is the denominator. And the derivative of the numerator. Numerator is e to the 4x. And we know that for e to the mx, the derivative of it, this is the sign of the derivative if you remember. First derivative, of course. So the derivative of it is m times e to the x, right? So here m is 4. So we write 4 times e to the 4x. That's the derivative of the numerator. Right? And then we know next we subtract the derivative, we keep the numerator and find the derivative of the denominator and subtract the product of that from the first product, right? So we keep the numerator, which is e to the 4x, and find the derivative of the denominator, which is x squared. What's the derivative of x squared? We know if we have anything of this format, the derivative of it is n times x to the n minus 1. So here for x squared, n is 2. So it's 2 times x to the 2 minus 1, which is 1. So you can write 2x. Any question from this? Before I go any further, any question? No questions at all? Okay, in the denominator, we have the denominator squared. We have the denominator x squared. And oh, sorry, I need to write the formula first. The denominator, whatever that is, we need to square it. So we have x squared here, and we need to square it. So that should be it. We can still simplify it, and we will simplify it, but any question up to this? Any question? It's not easy, I'm telling you. It's not difficult, but when you start with this, when you're doing it for the first time, it's really easy to make a mistake. You have to practice a lot. Okay? Any question from this? For the homework, you can have the formula in front of you, and you can use that. So memorizing the formula for the homework won't be required, but you need to understand what's going on here, how to do this, what's the significance of keeping this order, or how to find the derivative of these formats. You need to practice a lot of this, okay? Any question from this? As I said, we can still simplify it, and I will simplify it now. But before that, any question from the calculus part? Because we'll be just doing algebra now. Okay, looks like no question. So let's simplify it, and then we'll come back to it. So if we simplify it, we can factor out x from each term and e to the 4x from each term, right? If we do that, we have factored out x from this term, so we still have 1x because we had x squared here. If we factor out 1x, we still should have one more x here, right? We have factored out e to the 4x, so we only have 4 here. And for the second one, we have factored out e to the 4x, so we don't have anything from that part. From this part, we have factored out x, so we have 2. I'm just using some, doing some algebra, nothing else. And in the denominator, we have x to the 4th, and we can actually cancel out one of these. We have x to the 1 here and x to the 4th here. If we cancel out one of these, we get x cubed in the denominator, and it gets vanished. We have e to the 4x minus 2. This is our final answer. I've just done some algebra here, nothing else. The calculus part was done here. Any question from this? Any question you want me to answer? You want me to re-explain anything?